Let's move on now to the last section of Chapter 2, which is the slope as a rate of change. Now, we learned a lot about the slope in Chapter 1. Namely, it's like rise over run, it's the vertical change over the horizontal change, it's the change in y over the change in x, all of those good things. But because of the formulation, if you will, of what it is, that also means that it has some really important context for us, namely that it's a rate of change. So let's talk about what a rate of change is. So if you have a ratio of a to b, the fraction a over b, then the unit ratio is a ratio written when b is equal to 1. So that's what the rate of change is going to be. It's going to be a fraction. So for example, the temperature increased from 60 degrees Fahrenheit at 7 a.m. to 72 degrees Fahrenheit at 11 a.m. Estimate how much the temperature increased per hour. All right, so the first thing they want to know is what is the ratio of temperature increase over time? Okay, so let me bring that up real quick. There it is. Okay, so let's do a little bit here. So we want to know the change in y over the change in x, or in other words, temperature to time, because it says temperature increase over time. All right, so let me write that up. So temperature over time. Okay, now that's equal to, and this is where the fun begins, we're going to make a ratio out of it, right? So we need to think a little bit about how much it increased. It went from 60 degrees to 72 degrees. That means that we have a difference, an increase, if you will, of 12 degrees. Fahrenheit over 4 hours. And there you go. There's a ratio, right? The ratio of increase of temperature over time. Now the question becomes, what is the unit ratio? Because that's a ratio, all right, but it's not a unit ratio. Okay? So to make it a unit ratio, you need the denominator to be 1. And it currently isn't. It's currently 4. But we all know that, look, this one actually is pretty easy, but if it didn't work out so simply, you could just get a decimal. But we all know that this must be 3 over 1 because, right, 4 goes into 12 3 times. So there you go. So there's our unit ratio. So the bottom, the denominator is in 1 hour. Right? And again, if this didn't work out nicely, if it worked out to 3.5, then you'd write 3.5 over 1. It's one of the few times where a decimal is allowed in a fraction. All right? Okay, so there's ratio and unit ratio. Unit, again, uni, meaning 1, means the denominator is 1. So just on a side note, if this one had been, I don't know, oopsie, hold on. There you go. If this had been 3 over 2, oh gosh, there you go, 3 over 2, then for the bottom one you would say, let's be a little note over here, note. If it was 3 degrees Fahrenheit over 2 hours, then you would say over here, I gotta stop doing that. I'm pressing the wrong thing there. All right, so then you would say 1.5 over 1, right? Like that. So that's how to make a unit ratio with one that doesn't work out. So we just kind of add them in over there. All right. Okay, so, and again, rate of change is what you're finding, right? You're finding how the y changes over how the x changes, which is slope, right? So when you find that average rate of change, you're finding your slope, right? Then let's see here. So the number of animals used in research with pain or distress where no drugs were given for their relief declined approximately steadily from 103,000 animals in 2002 to 74,000 animals in 2006. Now this approximately steadily business means it's going linearly down, right? Approximately, so roughly. Find the average rate of change of the number of animals used in such research per year. Okay, so a couple of things. The average rate of change, why average? Why not just say the rate of change? Well, because it was approximate. This isn't perfect. It's not like it drops the same amount every year. It's that it just drops an average. And that's what you're trying to figure out. On average, how much does this drop per year? So we want the average rate of change. According to the formula in that little box, that's going to be equal to the change in y. Okay, now what's y for us? That might be a good thing to kind of make a note of over here. So note, not note, bite. All right, so note, it goes year, comma, 1,000 animals. Right? Those are your two variables. So again, X and Y, T and A, whatever letters you want to use, it doesn't matter. But you do have to know which one's your X and which one's your Y. That's important. And in most cases, calendar year, i.e. what year it is going to be your independent variable. You don't really have any control over the calendar year. All right, so it's going to be the change in Y. Y for us, here, I'm going to write down change in X. Now, Y and X is animals, so 1,000, I can just say animals, but we know it's got to be 1,000 animals over the change in year. All right, so that's our Y and that's our X. We set those up. All right, now that's equal to, let's see, now how did the animals change? You know what, we better write those points down. So in 2002, right here, they were 103 animals, or 103,000. So 103. And we just know that it's 1,000 animals. And then the other point is, let's see, in 2006, it was 74,000. Now, if you want, you can invent a starter year for yourself, but it's not really necessary for this particular one. So if you want, you can say years since 2000. 2000 be a good starter year. Then this is 2 then, and then this is 6. Again, it wasn't strictly required for this problem, but it doesn't hurt. You could make a starter year. I mean, it'll make things a little bit easier. All right, so t equals 0 is 2000. So then you have years since 2000 and the 1,000 animals that have been used on research. Again, you don't have to do it this way. If you want to do 2002, that's fine. But it always pays, as a general rule, to make things simpler for yourself. Okay, so if that's the case, then we can say our Y is 74. Oops, come back. 74, take away 103 over 6 take away 2. And again, if you use the 2006, it would just be 2006 take away 2002. But it'll still work. All right, then what? Well, we just have to find this. So this is negative 29, oopsie, negative 29 over 4, which if I use my calculator gets to negative 7.25. So they wanted to know the average rate of change, right? They didn't specify whether they wanted it as a fraction or a decimal or a unit ratio. They didn't really say. So technically this is correct with the negative 29 over 4, but to be honest with you, oops, that's 7.25. This is the one you're going to use most of the often, right? It's negative 7.2, and then you got to give it its unit. It's really over 1 if you want to know. Over 1. So what are its units? It's 1,000 animals, because that's your Y. 1,000 animals per year, right? Oops. There we go. All right. So let's see if that makes sense. You made some points, right, out of the data. Good. Then you went and found the average rate of change is the change in the Y, which was animals, over the change in year. So you subtracted the two Y values over the years. You got that. And then we made a unit ratio out of it. Again, not because it was required, but honestly, that's what you're going to do most of the time. And you're going to say, okay, every year we're losing 7.25, or we're using less, 7.25 thousand less animals per year for that kind of research. Make sure you put in those units, though. That's why it pays to kind of write this out for yourself. You say, really this was the change in thousands of animals, 1,000 animals over years, and that helps you with when you have to write it. And it also helps you if you had to interpret it, which I know they didn't ask for, but it pays to write it down. Every year, 7.25, let's see, 7.25 thousand less animals are used in this type of research. So let's just put it that way. Okay, less because it's negative, right? So it's going down. So they're using that many less animals every year, right? Or you could say the number of animals, I mean, that probably better. The number of animals used in this type of research decreases by 7.25 thousand. Something like that. That would also be good. All right. We made some notes up here kind of for our own sanity's sake. And then they didn't ask you for the interpretation, but I think it helps for us to kind of remind ourselves how to interpret that. Okay, let's move on. So next thing we have is D is the distance in miles that a student can travel, or excuse me, a student can drive in T hours. See the table? You're supposed to create a scattergram, then draw a linear model. So let me go do that. But basically you're going to go 0, 0, 1, 50, 2, and so on. There we go. So I've got the points down there. It said to create a scattergram, and then we're supposed to draw a linear model. Oh, I didn't do that. So you can kind of see there's a line. This is hardly a scattergram. I mean, there's nothing even scattered about it. So let me draw the line in there. I'll make it black so you can see it. All right. So we've got our points drawn and all that good stuff. Now we need to answer the other questions. Oopsie, that was not what I wanted to do. Hold on. There we go. So we're supposed to find the slope of this model, which hopefully you can see. The slope is the rate of change here. So your rise over your run. So let's see here. Slope is the change in, change in y. Okay, now y for us was distance. So it's going to be distance, or miles, let me put it that way. Change in miles over change in hours. Okay, change in y over change in x. But if you look at it, I mean, you don't have to even do the formula for this, but if you wanted to, I mean, you could. It'd be, let's see, 50 take away 0 over 1 take away 0, right? Which is 50 over 1. And the units for that are, should be obvious to anybody who's ever driven a car, miles over hours, i.e. miles per hour. There's your slope, 50. Oh, rats. All they wanted for this one was the 50 part. Oh, sorry. Okay, hold on one second. So they just want the 50 at this point. I just actually answered the other question down below because the 50 part is the slope, right? And then the rate of change is miles per hour. So 50, boom, right? y2 minus y1 over x2 minus x1. So change in miles, change in hours 50, or 50 over 1, which would just be 50. Okay. But when they want the rate of change, that's when you say, oh, it's 50 miles per hour. The way to write that in a different form, instead if you don't want to write 50 over 1 like that, you can just write 50 mph. mph is the unit for miles per hour. Right? So the slope is just the raw number. Slope doesn't have units. So let me take a note. Slope does not have units necessarily, right? It's just change in y over change in x, change in miles over change in hours. And then the rate of change part, rate of change has units. They're the same thing. They're the same number. It's just that the rate of change part is the slope within context, if you will. So this would be really more change in y over change in x, i.e. devoid of context, more or less. And then the rate of change part is where it has its context thrown back in, so it gets its units in. So in other words, what I'm trying to prove to you is that they're basically the same thing, that your slope is a rate of change, right? Slope is just rate of change with the units thrown in there. All right, a constant rate of change. If there's a linear relationship like there was in these ones, it'll be constant. It'll go up by the same amount every time. That steady increase, that's what slope is, right? Slope is that up and over, up and over, up and over. That's what slope is a measurement of. So if it has that steady rate like it does in this problem, then that shows that this was a linear model, which it was.